Hi all, today we will discuss about the behavioral design pattern. So behavioral patterns are concerned with algorithms and the assignment of responsibilities between objects. It describes not just patterns of objects or classes, but also the patterns of communications between them. So these patterns characterize complex control flow that is difficult to follow at runtime. And behavioral class patterns use inheritance to distribute behavior between classes, and behavioral object patterns use object composition rather than inheritance. So these helps to manage complex control flow by focusing on object relationships, and it also reduce coupling between objects. So the first type is chain of responsibility. So this avoid coupling the sender of a request to its receiver by giving more than one object a chance to handle the request. So chain the receiving objects and pass the request along the chain until an object handles it. So we can use chain of responsibility when more than one object may handle a request and the handler is not known a priori. The handler should be ascertained automatically. And if you want to issue a request to one of several objects without specifying the receiver explicitly, or the set of objects that can handle a request should be specified dynamically. So the participants are handler. This defines an interface for handling a request, and it implements the successor link optionally. And concrete handler handles request it is responsible for, and it can also access its successor. If the concrete handler can handle the request, it does so. Otherwise, it forwards the request to its successor. And client initiates the request to a concrete handler object on the chain. So when a client issues a request, the request propagates along the chain until a concrete handler object takes responsibility for handling it. So chain of responsibility has the following benefits and liabilities. The pattern frees an object from knowing which other object handles a request. So an object only has to know that a request will be handled appropriately. Both the receiver and the sender have no explicit knowledge of each other, and an object in the chain does not have to know about the chain structure. So chain of responsibility can simplify object interconnections, and chain of responsibility gives you added flexibility in distributing responsibilities among objects. We can add or change responsibilities or otherwise changing the chain at runtime. We can combine this with subclassing also. And receipt is not guaranteed. So since a request has no explicit receiver, there is no guarantee it will be handled. That is, the request can fall off at the end of the chain without ever being handled. So a request can also go unhandled when the chain is not configured properly. So next type is command. It encapsulates a request as an object and let the parameterize clients with different request, queue or log request, or support undoable operations. It is also known as action or transaction. So in this type, request, the client creates a concrete command object and specifies its receiver. An invoker object stores the object. The invoker issues a request by calling execute on the command. When commands are undoable, then concrete command stores the state for undoing the command, And the concrete command object invokes operations on its receiver to carry out the request. So this allows flexibility, and we can change the command dynamically, and we can undo or redo and request logging. So the participants are: command declares an interface for executing the operation, and the concrete command defines a binding between the receiver object and an action, and it also implements execute by invoking the corresponding operation, and client creates a concrete command object and sends it a receiver, and invoker asks the command to carry out the request. Receiver knows how to perform the operations associated with carrying out a request, and any class may serve as a receiver. So the consequences are: command decouples the object that invokes the operation from the one that knows how to perform it. And commands are first class objects. They can be manipulated and extended like any other object. And you can assemble commands into a composite command. An example is the macro command class. In general, composite commands are an instance of composite pattern. And it is easy to add new commands because you don't have to change existing classes. Next type is interpreter. So given a language, define a representation for its grammar along with an interpreter that uses the representation to interpret sentences in the language. So the participants are: abstract expression. This declares an abstract interpret operation that is common to all nodes in the abstract syntax tree. And terminal expression implements an interpret operation, and it is an instance required for every terminal symbol in a sentence. And non-terminal expression, this is one such class required for every rule in the grammar, and it maintains instance variables, and it also implements an interpret operation for non-terminal symbols. So interpret typically calls itself recursively. And context contains information that is global to the interpreter, and client builds an abstract syntax tree representing a particular sentence in the language, and abstract syntax trees assembled from instances of non-terminal expression and terminal expression classes. It also invokes the interpret operation. So the consequences: so because the pattern uses classes to represent grammar rules, you can use inheritance to change or extend the grammar. And existing expressions can be modified incrementally, and new expressions can be defined as variation on old ones. And implementing the grammar is easy. That is, classes defining nodes in the abstract syntax have similar implementations, and these classes are easy to write, and often their generation can be automated with a compiler or a parser generator. And complex grammars are hard to maintain. That is, the interpreter pattern defines at least one class for every rule in the grammar. Hence, grammars containing many rules can be hard to manage and maintain. So, other design patterns can be applied to mitigate this problem. But when the grammar is very complex, other techniques such as parser or compiler generators are more appropriate. And adding new ways to interpret expressions. That is, the interpreter pattern makes it easier to evaluate an expression in a new way. So next type is iterator. So this provides a way to access the elements of an aggregate object sequentially without exposing its underlying representation, and it is also called cursor. So the key idea in this pattern is to take the responsibility for access and traversal out of the objects and put it into an iterator object. So iterator class defines an interface for accessing the elements, and iterator object is responsible for track of the current element. That is, it knows which elements have been traversed already. So the participants are: iterator defines an interface for accessing and traversing elements. Concrete iterator implements the iterator interface and also keeps track of the current position. Aggregate defines an interface for creating an iterator object, and concrete aggregate implements the iterator creation interface to return an instance of the concrete iterator. So the iterator pattern has three important consequences. It supports variations in the traversal of an aggregate. So complex aggregates may be traversed in many ways. For example, code generation and semantic checking involve traversing parse trees. So code generation may traverse the parse tree in order or pre-order. So iterators make it easy to change the traversal algorithm. Just replace the iterator instance with a different one. So we can also define iterator subclasses to support new traversals. And iterators simplify the aggregate interface. That is, iterators traversal interface obviates the need for a similar interface in aggregate. So simplify the aggregator's interface. And more than one traversal can be pending on an aggregate. An iterator keeps track of its own traversal state. Therefore, you can have more than one traversal in progress at once. Next type is mediator. So this define an object that encapsulates how a set of objects interact. And mediator also promotes loose coupling by keeping objects from referring to each other explicitly, and it also lets you vary their interaction independently. A mediator is responsible for controlling and coordinating the interactions of a group of objects. The mediator serves as an intermediary that keeps objects in the group from referring to each other explicitly, and the objects only know the mediator. So it reduces the number of interconnections and also reduce complexity. We can use the mediator pattern when a set of objects communicate in well-defined but complex ways. So the resulting interdependencies are unstructured and difficult to understand, or reusing an object is difficult because it refers to and communicates with many objects, or a behavior that is distributed between several classes should be customizable without a lot of subclassing. So there are three participants in a mediator. So mediator defines an interface for communicating with colleague objects, and concrete mediator implements a cooperative behavior by coordinating these colleague objects, and it also knows and maintains its colleagues. And colleague classes means each colleague class knows the mediator object, and each colleague communicates with its mediator whenever it would have otherwise communicated with another colleague. And colleagues send and receive requests from a mediator object, and mediator implements the cooperative behavior by routing requests between the colleagues. So the mediator pattern has some benefits and drawbacks. So first of all, it limits subclassing. That is, a mediator localizes behavior. Otherwise, it would be distributed among several objects. So changing this behavior requires subclassing mediator only. Colleague classes can be reused. and it decouples colleagues. That is, a mediator promotes loose coupling between colleagues, and we can vary and reuse colleague and mediator classes independently. Then it simplifies object protocols. That means a mediator replaces many-to-many interactions with one-to-many interactions between mediator and colleague. So one-to-many relationships are very easier to understand, maintain, and extend. And it abstracts how objects cooperate. So make mediation an independent concept and encapsulating uh, focus on how objects interact apart from their behavior. So it helps clarify how objects interact in a system, and it centralizes control. That is, the mediator pattern trades complexity uh, of interaction for complexity in the mediator. So a mediator encapsulates protocols, so it can become more complex than in an individual colleague. So this can make the mediator itself like a monolith, so it is hard to maintain. That is the disadvantage. Next type is memento. So the intent of memento is without violating encapsulation, capture and externalize an object's internal state so the object can be restored to the state later. And it is also known as token. We can use the memento pattern when a snapshot of some portion of an object state must be saved so that it can be restored to that state later. And a direct interface to obtain the state would expose the implementation details and break the encapsulation. So there are three participants in a memento type. So memento stores internal state of the originator object. So the memento may store as much or as little of the originator's internal state, and it also protects against access by objects other than the originator. And mementos have effectively two interfaces. Then originator creates a memento containing a snapshot of its current internal state. It uses the memento to restore its internal state also. And caretaker is responsible for the memento's safekeeping, and it also never operates on or examines the contents of the memento. And a caretaker requests a memento from an originator, and it holds it for a time and then passes it back to the originator. So sometimes the caretaker won't pass the memento back to the originator because the originator might never need to revert to an earlier state. So mementos are passive. Only the originator that created a memento will assign or retrieve its state. So the memento pattern has several consequences. So memento avoids exposing information that only an originator should manage, but that must be stored outside the originator. So the pattern shields other objects from complex originator internals, thereby preserving encapsulation boundaries. And it simplifies originator. So originator keeps, in other encapsulation preserving designs, originator keeps the versions of internal state. So that puts storage management burden. But here clients manage the state they ask for, simplifies originator and keeps clients from having to notify originators when they are done. And using mementos might be expensive. So originator state is cheap, the pattern might not be appropriate, so mementos might incur considerable overhead if originator must copy large amounts of information to store in the memento. So unless encapsulating and restoring originator state, the pattern might not be appropriate. then defining narrow and wide interfaces. So it may be difficult in some languages to ensure that only originator can access the mementos state. And hidden costs are there in caring for mementos. So a caretaker is responsible for deleting the mementos. So the caretaker has no idea how much state is in the memento. So hence, an otherwise lightweight caretaker might incur large storage costs when it stores mementos. Next type is observer. The intent of an observer is to define a one-to-many relationship or dependency between objects so that when one object changes state, all its dependents are notified and updated automatically. So this observer type is also called dependence or publish subscribe. The observer pattern describes how to establish these relationships. So the key objects in this pattern are subject and observer. A subject may have any number of dependent observers. All observers are notified whenever the subject undergoes any state changes. And each observer will query the subject to synchronize the state with the subject's state. And this kind of interaction is all called publish subscribe. So the subject is the publisher of notifications. It sends these notifications without having to know who its observers are. Any number of observers can subscribe to receive notifications. So we can use the observer pattern in any of these situations, like when an abstraction has two aspects, one independent on the other, and encapsulating these aspects in separate objects let you vary and reuse them independently. And when a change in one object requires changing others, and you don't know how many objects need to be changed. And when an object should be able to notify the objects without making assumptions about who these objects are. And in other words, you don't want these objects tightly coupled. So in this type, there are four participants. So the subject knows its observers. Any number of observer objects may observe a subject, and it also provides an interface for attaching and detaching observer objects. Then observer defines an updating interface for objects, and concrete subject stores the state of interest, and it also sends a notification to its observers when its state changes. And concrete observer maintains a reference to a concrete subject object, and it also stores the state, and it implements the observer updating interface. And this concrete subject notifies its observers whenever a change occurs that could make the observer state inconsistent with its own. And after being informed, a concrete observer object may query the subject for information. So concrete observer uses this information to reconcile its state. The observer pattern lets you vary subjects and observers independently, that we know, and we can reuse subjects without reusing their observers and vice versa. And we can also add observers without modifying the subject or observers. So there are some benefits and liabilities of observer pattern. First is abstract coupling between subject and observer. So we know that subject and observer are not tightly coupled here. So they can belong to different layers of abstraction in a system. So a lower level subject can communicate and inform a higher level observer and keep the system's layering intact, and vice versa. Then support for broadcast communication. So the notification is broadcast automatically to all interested objects that subscribed to it. The subject does not care how many interested objects exist, but it is only responsible to notify its observers. And it gives you the freedom to add and remove observers at any time. And unexpected updates. So sometimes some operations on the subject may cause a cascade of updates to observers and their dependent objects. So this causes some problem. That means a simple update protocol provides no details on what changed in the subject. So this may cause some problems. Next type is state. So this allows an object to change its behavior when its internal state changes, and the object will appear to change its class, and it is also called objects for states. So we can use the state pattern in either of these cases. First is an object's behavior depends on its state, and it must change its behavior at runtime depending on that state. Or operations have large multi-part conditional statements that depend on the object state, and this state is usually represented by one or more enumerated constants, and several operations will contain the same conditional structure. So the state pattern puts each branch of the conditional in a separate class, and this lets you treat the object state as an object, and it can vary independently from other objects. In these two cases, we can use state pattern. So there are three participants. First is context. It defines the interface of interest to clients, and it also maintains an instance of a concrete state subclass. It defines the current state. And state defines an interface for encapsulating the behavior. And concrete state subclasses, each subclass implements a behavior associated with the state of the context. So this context delegates state-specific request to the current concrete state object. And context may pass itself as an argument to the state object, and it had to handle the request. And this lets the state object access the context. And context is the primary interface for clients, and clients can configure a context with state object. And once a context is configured, then clients don't have to deal with the state objects directly. Either context or concrete state subclasses can decide which state succeeds another and under what circumstances. So the state pattern has these consequences. It localizes state-specific behavior and partitions behavior for different states. That is, the state pattern puts all behavior associated with a particular state into one object. And because all state-specific code stays in a state subclass, new states and transitions can be added easily by defining new subclasses. And it makes state transitions explicit. So when an object defines its current state, its state transitions have no explicit representations. It only show up as assignments to some variables. So introducing these separate objects for different states makes the transitions more explicit. Then state objects can be shared. If state objects have no instance variables, that is, the state they represent is encoded entirely in their type, then context can share a state object. Next type is strategy. Strategy define a family of algorithms, encapsulate each other, and make them interchangeable. And strategy lets the algorithm vary independently from clients that use it. It is also called policy. So we can use the strategy pattern when many related classes differ only in their behavior. So strategies provide a way to configure a class with one of these many behaviors. And you need different variants of an algorithm. For example, you might define algorithms reflecting different space or time trade-offs, and strategies can be used when these variants are implemented as a hierarchy of algorithms. And an algorithm uses data that clients should not know about it, and we can use the strategy pattern to avoid exposing complex algorithm specific data structures. And if a class defines many behaviors and these appear as a multiple conditional statements in their operations. So instead of many conditionals, we can move related conditional branches into their own strategy class. So there are three participants here. So strategy declares an interface common to all supported algorithms, and context uses this interface to call the algorithm defined by concrete strategy. And concrete strategy implements the algorithm using strategy interface, and context is configured with a concrete strategy object. It also maintains a reference to a strategy object, and it also defines an interface that let strategy access its data. And strategy and context interact to implement the algorithm. So a context may pass all data required by the algorithm to the strategy when the algorithm is called. So the context can pass itself as an argument to the operations, and it lets strategy call back on the context when required. And a context forwards requests from its clients to its strategy. Clients usually create and pass a concrete strategy object to the context, and clients interact with the context, and there will be a family of concrete strategy classes for a client to choose from. So there are various consequences in this type. So first is families of related algorithms. So hierarchies of these strategy classes define a family of algorithms or behaviors for context to reuse, and inheritance can also help figure out the common functionality of the algorithms. And an alternative to subclassing. So inheritance offers another way to support a variety of algorithms or behaviors. So encapsulating the algorithm in separate strategy classes lets you vary the algorithm independently. So this will be easier to switch, understand, and extend. Then strategies eliminate conditional statements. So strategy pattern offers an alternative to conditional statements for selecting desired behavior. Then a choice of implementations. So strategies can provide different implementations of the same behavior. So the client can choose among these. Then clients must be aware of different strategies. So the pattern has a potential drawback in, like, a client must understand how strategies differ before it can select the appropriate one. So clients might be exposed to implementation issues. So you should use strategy pattern only when variation in behavior is relevant to clients. Then communication overhead between strategy and context. So there will be communication overhead between strategy and context, because the strategy interface is shared between all concrete strategy classes, and that means there will be times when context creates and initializes parameters that never get used. So if it is an issue, then we will need a tighter coupling between strategy and context. Then increase number of objects. So strategies increase the number of objects in an application. So sometimes we can reduce this by implementing strategies as some stateless objects, and that context can share. Next is template method. So template method define the skeleton of an algorithm in an operation, differing some steps to subclasses, and template method lets subclasses redefine certain steps of an algorithm without changing the structure of the algorithm. So we can use the template method pattern to implement the invariant parts of an algorithm once and leave it up to subclasses to implement the behavior. And when common behavior among subclasses should be factored and localized in a common class to avoid code duplication. So this is a good example of refactoring to generalize. And you can first identify the differences in the existing code and then separate the differences into new operations, and finally you can replace the different code with the template method and it calls any of these new operations. Or we can also use to control subclasses extensions. So you can define a template method that calls hook operations at specific points. So this permits extensions only at those points. So there are two participants, abstract class and concrete class. So abstract class defines abstract primitive operations that concrete subclasses define to implement the steps of an algorithm. This also implements a template method defining the skeleton of an algorithm. So the template method calls primitive operations and operations defined in abstract class or those or other objects. The concrete class implements the primitive operations to carry out subclass specific steps of the algorithm. So concrete class relies on abstract class to implement the invariant steps of an algorithm. So template methods are a fundamental technique for code reuse, and they are particularly important in class libraries because they are the means for factoring out the common behavior in library classes. So template methods lead to an inverted control structure called Hollywood principle. That is, don't call us, we will call you. So this refers to how a parent class calls the operations of a subclass and not the other way. So template methods call the following kind of operations like concrete operations, concrete abstract class operations, primitive operations, factory methods, and hook operations. So it is important for template methods to specify which operations are hooks and which are abstract operations. Abstract operations can be overridden, but hook operations may be overridden. To reuse an abstract class effectively, uh, the operations are designed for overriding. And a subclass can extend a parent class operation by overriding the operation. So next type is visitor. So this pattern represents an operation to be performed on the elements of an object structure. So visitor lets you define a new operation without changing the classes of the elements on which it operates. So we can use this visitor pattern when an object structure contains many classes of objects with differing interfaces and you want to perform operations on these objects that depend on their concrete classes, or many distinct and unrelated operations need to be performed on objects in an object structure and you want to avoid polluting their classes with these operations. So visitor can be keep related operations together, and when the object structure is shared by many applications, we can use visitor to put operations in those applications that need them. And It can be also used in the classes defining the object structure that rarely changes, but you want to define new operations. So changing the object structure classes requires redefining the interface to all visitors. So it is very expensive operation. So if the object structure classes changes often, then we can use this visitor pattern to define the operations in those classes. So there are many participants in this style. First is visitor. It declares a visit operation for each class of concrete element in the structure. So the operation's name and signature identifies the class that sends request to the visitor, and it lets the visitor determine the concrete class, and also the visitor can access the element directly through a interface. And concrete visitor implements each operation declared by the visitor, and each operation implements a fragment of the algorithm. And concrete visitor also provides the context for the algorithm, and it also stores the state, local state. So this state can be used to accumulate results during the traversal of the structure. And element defines an accept operation that takes a visitor as an argument. Then concrete element implements an accept operation and it takes a visitor as an argument. Then object structure can enumerate its elements. It can also provide a high level interface to allow the visitor to visit the elements, and it may either be a composite or a collection such as a list or a set. So a client that uses the visitor pattern must create a concrete visitor object and then traverse the object structure visiting each element with the visitor. So when an element is visited, it calls the visitor operation and the element supplies itself as an argument, and visitor can access its state if necessary. Then the benefits and liabilities are: visitor makes adding new operations easy. So visitors makes it easy to add operations, and you can also define a new operation by adding a new visitor. And if you can also change each class to define a new operation. And a visitor gathers related operations and separate unrelated ones. So related behavior is not shared over the classes, but it is localized in a visitor. And unrelated sets of behavior are partitioned in their own visitor subclasses, and it simplifies both classes defining elements and algorithms. Then adding new concrete element classes is hard. So the visitor pattern makes it hard to add new subclasses of elements. And visiting across class hierarchies. So visitor can visit objects that don't have a common parent class. We can add any type of object to a visitor interface. Then accumulating state. That is, visitors can accumulate state as they visit each element in the structure. So without a visitor, the state would be passed as extra arguments, or they might appear as global variables. And breaking encapsulation. So the pattern visitors approach assumes concrete element interface is powerful, but the pattern forces you to provide public operations that can access the internal state of the element, which can compromise its encapsulation.